Hello and welcome back. My name is Dr. Mark Taylor, and this is the third of a series of videos reviewing the Delaware Tech Physics 111 Exam 3 Preparation and Practice Exam on Waves and Sound. And here we're going to deal with wave calculation problems. And when it comes to wave calculation problems, there are only a couple things you need to know. Number one, you need to know how to look at a graph of a transverse wave and determine the wavelength if the wave is graph versus length, and determine the period if the wave is graph versus time. And then in terms of the actual calculations, there are really only two formulas you need to deal with. One of them is the formula that relates frequency to period, and these are reciprocals, so frequency equals 1 over period, and period equals 1 over frequency. These are the same formula, just rearranged. The second formula you need to know is the speed formula. And this is true for any kind of wave. The speed of the wave is equal to its frequency times its wavelength, or its wavelength times its frequency. So we have just two formulas to deal with for all of these standard calculation problems. All right, let's take a look at the first problem. If a wave has a wavelength of 0.0132 meters and a frequency of 56,700 hertz, what is its speed? Well, we know the wavelength is 0.0132 meters, and we know the frequency is 56,700 hertz. And remember, hertz is the same thing as seconds to the minus 1, or 1 over seconds. And if we use the second formula, the speed is just equal to the frequency times the wavelength. Well, that's 56,700 hertz, or per second, or 1 over seconds, or seconds to the minus 1, times 0.0132 meters. And when we multiply these out, we get a numerical answer of 748. Well, what are the units? Well, it's meters per second. Remember, the hertz is per second. So our final speed is 748 meters per second. The next problem. What is the period of a wave with a frequency of 54 hertz? Well, remember, the period is just 1 over the frequency. It's the reciprocal of the frequency. 1 over 54 hertz, and remember, hertz, again, is per second, or 1 over second. So when you take the reciprocal, and the numerical value of the reciprocal is 0.0185, well, this is 1 over seconds, so we get our seconds back, and that makes sense because period is a measure of time, so our answer will be in seconds, 0.0185 seconds. The next question, what is the frequency of a wave with a period of 0.125 seconds? Well, this is the same formula we just used, just in reverse. The frequency is equal to 1 over the period. The frequency is the reciprocal of period. The period is the reciprocal of frequency. Taking 1 over the period, 0.125 seconds, and we end up with the numerical value of 8. And what is our unit? Well, our unit is 1 over seconds, but 1 over seconds is the same thing as hertz. And remember, we're going to use as our standard unit of frequency the hertz, so our answer is 8 hertz. The next question, if a wave has a wavelength of 0.000345 meters, so write that down, wavelength equals 0.000345 meters, and a period that's capital T, of 0.00564 seconds, what is its speed? Well, we know speed is frequency times wavelength. Well, we have the wavelength, but we don't have the frequency. But we know that frequency is 1 over the period, and we do have the period. So 1 over 0.00564 seconds. We plug that into our calculator, and our numerical value is 177.3. Well, what are the units? Well, it's 1 over seconds, or hertz. And when you're doing calculations, sometimes it's easier to leave it as the 1 over seconds, but it really doesn't matter as long as you remember hertz is 1 per second, or second to the minus 1, any one of those variations. And now we have the information to solve for our speed. Speed is our frequency, which is 177.3 hertz or per seconds. I'll leave it as per seconds, times our wavelength, 0.000345 meters. We plug this into our calculator, and we get a numerical value of 0.0612. And remember, whenever you're doing multiple calculations, don't use a rounded value of your first number when you're going into the second calculation. Use a fairly unrounded version. That way you don't get any errors that we refer to as rounding errors. All right, so what are our units? Well, we have meters and we have per second. So it's meters per second. So our speed of our wave is 0.0612 meters per second. All right, continuing on. If a wave has a speed of 926 meters per second, so we'll just write that down. Our speed is 926 meters per second, and a wavelength of 62 meters. What is the frequency? Well, we have two formulas for frequency. We have a frequency equals 1 over period, but we don't have the period. And we have a formula for speed that involves frequency and wavelength. And we have speed and wavelength. So we're going to use this formula, and we'll plug these numbers in for the speed and wavelength. We know the speed is 962 meters per second, and we know that equals our unknown frequency times our known wavelength of 62 meters. We divide both sides by 62 meters, and that cancels the 62 meters on the right side, leaving only the frequency. And now we have this relationship that we plug into our calculator, and we end up getting a numerical value of 14.9. What are our units? Well, it's frequency, so we know our units are going to be hertz. But if we want to convince ourselves it's hertz, we can look here. We have meters per second divided by meters. Well, if you had meters per second divided by meters, the meters cancel out, and you're just left with a blank space, which we fill in with a 1, over seconds. So that's the same thing as 1 over seconds, or per second. So our answer is 14.9 hertz. The next question. If a sound wave has a speed of 341 meters per second, and that's a pretty typical speed of sound. Speed of sound averages about 343 meters per second at room temperature at sea level. And we also have a frequency of 222 hertz. Keeping in mind, hertz is the same thing as 1 over a second. What is the wavelength? Well, we have one formula that involves wavelength. Speed equals frequency times wavelength. We know the speed, We know the frequency, we just have to calculate for the wavelength. So using that formula, we fill in the numbers. 341 meters per second equals our frequency, which is 222 hertz, or 222 per seconds, times our unknown wavelength. We divide both sides by 222 hertz. And I'm going to rewrite the 222 hertz on the left side of the equation, reminding you that it's also equal to 1/seconds, or per second. These cancel out, and we end up with our wavelength is equal to this expression. And we plug that into our calculator. We get a numerical value of 1.536. Well, what are our units? Well, we're asking for wavelength, so our units should be a unit of length. And the only unit of length we have in this equation is meters. Remember, speed is in meters per second. So this is going to be in meters. And if you want to convince yourself, we're actually dividing meters per second divided by 1 per second. The seconds cancel, and all you're left with is meters over 1, which is just meters. So our wavelength is 1.536 meters. Our next question asks, if a sound wave has a speed of 335 meters per second, 335 meters per second, and a wavelength of 0.131 meters, just get in the habit of writing down the parameters that you know from the problem. What is its frequency? Well, again, we have two formulas for frequency. Frequency is 1/period, but we're not given the period, so we can't use that one. And we also know that the wave speed is equal to frequency times wavelength. And we're asked for frequency, and we know the speed, and we know the wavelength. We plug those numbers in. Our speed is 335 meters per second. Equals our unknown frequency times our known wavelength of 0.131 meters. We divide both sides by 0.131 meters. This term cancels with itself, leaving only frequency is equal to this expression. We plug that into a calculator, and we get a value of 2,557. It's a frequency, so we know our answer is going to be in hertz, but we can check it. We're actually dividing meters per second by meters. Well, what happens when you get rid of the meters? You're left with per second, 1/seconds. And that makes sense because that's the same as a hertz. So that's our answer, 2,557 hertz. Next question. Consider the graph of a wave shown below. Now you see there's a particular type of wave. The first thing you should notice is this is a transverse wave. It's going up and down with crests and troughs. We can even label our crests and we can label our troughs. And we should note that this particular graph of a wave is versus time. So these coordinates here on the x-axis are time units in seconds. And that means we can get the period by analyzing this wave. And in fact, the first question says, what is the period of this wave? Well, you're not going to be doing some calculation from frequency. You're literally going to measure it. And you can measure it, whatever repeating unit of a wave you spot here. So you can go crest to crest. You can go trough to trough. Well, going from crest to crest is pretty easy because this crest is right at 0.10 seconds, and this crest is right at 0.40 seconds. So our period will be the difference between the two. 0.40 seconds minus 0.10 seconds, which means our period, our full amount of time for 1 full oscillation is 0.30 seconds. That's our period. Part B, what is the frequency of the wave? Well, we can just calculate that from the period. If you have the period, you can calculate the frequency. If you have the frequency, you can calculate the period. 1 over period, or the reciprocal of period, is your frequency. 1 over 0.30 seconds. We plug that into a calculator, we get 3.333 repeating, and this should be enough threes. We'll add one more just to be on the safe side. And the units are 1 over second. Well, 1 over second is the same thing as hertz, and we know that's correct because we're calculating a frequency, and we know the units are in hertz. So our answer is 3.33, or you can throw in another 3 hertz. And the last part of this question says, if the wave has a speed of 712 meters per second, what is its wavelength? All right, well, we know the speed is 712 meters per second. We don't know the wavelength, but we do know the frequency. We just calculated it. Frequency is 3.33. We'll add an extra 3 in there. Hertz, or per second, whichever way you want to write it. So we can use our speed equation. Speed equals frequency times wavelength. We know the speed, 712 meters per second. We know the frequency, 3.333 hertz, or per second. And we have an unknown wavelength. This up just a little bit. And we divide both sides by the 3.333 hertz, or 3.33 per seconds. 3.333 hertz, or per seconds, whichever way you want to write it, per seconds. These cancel out each other, and we're left with this expression, which is equal to our wavelength. We plug that into our calculator, and we get a value of 214. This is a wavelength, so our answer should be units of length. The only unit of length in here is meter. But if we look at it, we're taking meters per second and dividing it by per second. Well, that just leaves us with meters. So our wavelength is 214 meters. Next question. Consider the graph of a wave shown below. So we have another wave, and you'll notice this is another transverse wave, and it is also versus time. Anytime you see a wave drawn versus time, think, oh, I can get the period, and that means I can calculate the frequency. If you see the wave versus length or distance, that means you can measure the wavelength and use that in some calculation. Okay, so part A says label all crests and troughs, and we've done this before. So crests are going to be CR, and troughs, there's only one trough visible. You'll notice this isn't quite all the way down to the trough, and neither is that, so we're not going to label it a trough. So we have 2 crests visible and 1 trough visible. Part B says label 1 amplitude with a capital A. Well, the amplitude is the height of a crest, so it's this height. That would be that length between the center equilibrium point and the crest. That's the amplitude. Or you could have picked between the equilibrium point and a trough. That's also an amplitude. Or you could have picked this other amplitude rising up to a crest. Now, part C says measure that amplitude. All right. Well, the bottom of the amplitude is easy. That's right at 0. The top, you'll notice, is right here. It's midway between 0.04 centimeters and 0.06 centimeters. So we'll just call it 0.05 centimeters and that's of course minus 0. So the amplitude is 0.05 centimeters. Make sure you look at the unit for the displacement when recording the amplitude. Part D says label one period with a capital T on the above graph. So this is a wave graph versus time, so we can find the period on it. If this was versus length, as I mentioned before, we would be able to find the wavelength, but we can find the period on this type of graph. And the period is the length of time for one full cycle. It's how many seconds per cycle. Remember, it's the inverse of frequency. Frequency is how many cycles per second. Period is how many seconds per cycle. So we have to find one cycle. Well, a cycle would be the length between two consecutive crests or two consecutive troughs, but we only have one trough in here, so we have to use the crests. So it's essentially the amount of time between this crest and this crest. And you'll notice the first crest is at 1 second marker, and the second crest is at the 4 second marker. So we can label our period as being the amount of time between these two, and we'll label that with a capital T, and then we're asked to measure the period. Well, the period is the difference in those times. It's 4 seconds minus 1 second, and therefore the period is 3 seconds. Part F says calculate the frequency. Well, we can calculate frequency from period. It's the reciprocal of period, 1 over period. So it's 1 divided by 3 seconds. 1 over 3, or 1/3, is 0.333 repeating. I'll give it 3 threes here. And the unit is 1 over second, but we know frequency is also in units of hertz, and hertz is the same thing as 1 over second. So our frequency is 0.333 repeating hertz. And yes, there are very specific rules for how to round numbers once you've calculated them, but we don't cover that in this course. And the last part of this question says, if the wave speed is 2,560 meters per second, what is the wavelength? Okay, well, we have information. We have the speed is 2,560 meters per second. And we're asked for the wavelength. Well, we have a formula where we have speed equals frequency times wavelength. We're given the speed, but we just calculated the frequency. So we can calculate the wavelength using this formula. Our frequency is 0.333 hertz. But keep in mind, whenever you're using a number that was previously calculated and rounded, you really should be using the unrounded version when you do your new calculation using that number. So here we have this formula. Let's plug in numbers. The speed is 2,560 meters per second. That's equal to our frequency of 0.333, and that goes on forever. I'll just put a line there to remind us that it's repeating. Hertz times our unknown wavelength. We divide both sides by the frequency in order to get rid of the number on the right side of the equation. We do that on the left side as well. 0.333 repeating hertz, which is really per second. These cancel, and we end up with a wavelength that equals, and you may get a number that's slightly different, but that's because I'm going to use 0.33333, many threes, and if I do that, I end up with a value of 7680 as my numerical value for the wavelength. You'll notice the only length unit in here is meters, and in fact, if I divide meters per second by per second, remember hertz is per second, I'll end up with meters. So my wavelength is 7,680 meters, If you have a value that varies a little bit because you rounded the 0.333, that's perfectly fine. I'm not going to mark off for that. Again, we don't cover rounding numbers in this course. And with this, we'll stop here.